All right. So why don't we get going then? Welcome, everyone, to our monthly Lunch and Learn webinar. This one is totally in the circular water economy theme, resource recovery, valorization, whatever you want to call it, to the maximum extent, byproducts that are beneficial and replace commercial products that require energy and effort to produce, not to mention generating greenhouse gas emissions. So I think you're going to really enjoy this presentation today. Just a few housekeeping items before we get started. Everyone should be muted when you join. I'm going to ask you to stay on mute until the end of the presentation when you can unmute and ask questions directly. I am recording this session and the link and the slide presentation will be provided to everyone who signed up for the webinar. There is a Q&A function at the bottom of your screen, or you can use the chat if you prefer. I'll be keeping an eye on that, so feel free to type in any questions or comments as you think of them. But again, we're saving plenty of time at the end for questions and discussion. So I want to start out with a huge shout out to our sponsor for today's webinar, Underwood Engineers. Underwood is a full service civil and environmental engineering firm with its main offices in New Hampshire, Portsmouth, one of our favorite annual conference locales, and also Concord. And they maintain licenses in Maine, Massachusetts, and Vermont. With decades of experience working with state and municipal governments, Underwood Engineers is one of New England's most experienced and respected engineering resources. And this topic is right up their alley. The Underwood team works shoulder to shoulder with clients to evaluate challenges, identify solutions, and implement long-term outcomes for a sustainable future. Underwood has a portfolio of projects that span typical challenges of leading-edge treatment facilities tackling emerging contaminants. Underwood has been a great NEBRA member for a while now, with some staff engaged on our committees. So thanks again to Underwood for sponsoring this webinar. Remind me to talk about the BioHub later, but right now I want to get going so we don't run out of time. So now I'm happy to introduce our presenter today, Stefan Albers. He's the CTO and co-founder of Living Ink Technologies. He has a BS and a PhD from Colorado State University and an MS from the University of Illinois, Urbana-Champaign. His PhD research focused on engineering cyanobacteria for commercial projects with expertise in biological engineering, intellectual property, and early stage company development. He led the faculty startup program at Colorado State University Strata from 2016 to 2021. And Dr. Albers now heads Living Ink's R&D team, manages the company's IP portfolio, and collaborates with the U.S. National Science Foundation and the Department of Energy on grants through those agencies. I think you're going to find this very interesting. I know you will have some questions, so let's get going. I'm going to stop sharing my screen, and Dr. Albers, you
All
can
right.
take right over there.
All right. Janine, that was nicer than I expected, so I appreciate that. Thank you. Let's see. Let me make sure we got the right screen going here. Can
And
everyone
just
see my
swap
full screen?
displays.
Okay,
Yep. Beautiful. Looks great.
awesome. Well, thanks again, Janine. That's a great intro. I appreciate it. Hello, everyone. My name is Steve Albers. I'm the Chief Technology Officer and co-founder of Living Ink Technologies. So we're a company that is based in Colorado. So we're just north of Denver by about 20 miles. And we convert waste material into usable carbon black. So I'll introduce the company and just give you a sort of a high level discussion around that. And then I'll dive a little into our technology and where we'd love to take our technology and how we might be able to engage with folks from the audience in trying to move this technology forward. So thanks for joining. I appreciate you taking the time to do this today. So we make color from living carbon and value from waste. And I love starting things off by just saying, stop what you're doing, take a look around the room that you're in, and notice how much black is in this world. You know, I don't, I never did this until I started asking this question, and you start looking around, it's everywhere, right? And black is a majority of the colorants that are used in this world, partially because it's cool, right? Black tie events. but mostly for us science nerds in the audience, it does a great job of capturing UV light and and converting it into heat. And that's really important for products as they survive out in this world. And so it's caught on. We make a lot of products with black pigment in it. And so carbon black truly is everywhere. The majority of carbon black is actually, you'll see on a daily basis outside. The tires that are installable on all the equipment in cars on the road. The Michelin Man is actually white, right? And natural rubber is white. Engineers figured out to put carbon black in there to protect that rubber from degradation of UV light. So it's just kind of crazy to think about. And this is really the core of what we're focused on at Living Ink. Like I said, it's everywhere, right? And we know it's in paints, inks, rubber automotive, but the apparel, textile. Janine's got some on right now. Electronics, she's got that too. Paper packaging, leathers, and even cosmetics. You'll find carbon black in. And so it's a problem because it is all made from petroleum. Over 99% of the black in this world is made from carbon black, and it's essentially soot. So they'll spray fractions of heavy oil into a furnace and collect the soot, literally shovel the soot out of there and move it into a multitude of different grades. But huge emissions associated with capturing that material and converting that material. We know that there are polyaromatic hydrocarbons in that material, at times heavy metals, other chemicals of concern, and it's got a poor consumer perception, and that's you'll think about that quite a bit when you think about the apparel and the cosmetics and things like that. That one really resonates in those markets. And there are increasing regulations around this material. So what do we do at Living Ink? We turn waste into value, right? And so we take waste materials, waste biomass from a multitude of sources, but you guys are probably very aware of the waste material that is of biological origin coming out of different production processes. We take that material and we convert it into a carbon black that's usable. It's essentially biochar, but we do have some intellectual property that allows us to make a material, a pigment particle that actually can be used in these different markets. I love the joke, and maybe some of you won't. um, Biochar is good at everything but making money. And I think that one resonates quite a bit with biochar. So biochar is a cool product. It's carbon negative. It captures the carbon in biomass, but no one can really figure out how to monetize it. Our intellectual property puts a little spin on this and allows us to actually make a very viable downstream product. So I'll talk a little about that. But what we do is that we capture biomass from a lot of waste sources and convert it into carbon black. So it reduces waste. Well, first and foremost, we're identifying waste streams where people are paying to get rid of that material and figuring out how to decrease the tipping costs, if not eliminate the tipping costs, if not provide revenue for those materials, while making a carbon negative product that's safe and has performance equivalency. So that's a really important piece that we're working on is you can use our pigments to capture UV light and burn it off as heat because we are concentrating carbon. We're essentially carbon black, just made from a different process. So that one's really cool. You'll see a lot of biological products that tout a replacement capability, but when you really push it up against the performance characteristics in that market, they lose. And that's unfortunate because let's be honest, engineers are just really good at their jobs and makes really cool things for use in a lot of products. And nature has a hard time keeping up. This product is not the case. It is performance equivalency. And so, we can take waste out of waste lagoons. So probably something that you guys are pretty comfortable with, the whole concept. What we have been doing lately is taking actually waste from breweries. And that one's kind of fun because they get to go hang out at breweries often. So that one is pretty cool. But a lot of the waste yeast that comes out of large breweries, think Anheuser-Busch, think Coors, it's pretty hard to valorize that material because it's so wet. And we've been working on scaling up a pilot project to demonstrate that we can do that with Anheuser-Busch's material, which is really exciting. Our origins are algae, of course. We are science nerds. I got a PhD studying algae, so we started with algae. The problem is there's not a lot of algae out there that actually is concentrated and from a uniform source. So we work with quite a few groups to try to understand how we concentrate algae because algae is such a great story. But currently we're using algae. So we can take waste biomass from a lot of different sources and have tested quite a few sources through grants that we've received through the Department of Energy, the National Science Foundation, and states and regions. One of the great things about this material is that we can divert that material from going to landfills and land application in a way that actually upcycles it in a true upcycling process. So this one resonates with a lot of folks, I'm sure, with you guys, especially up in the Northeast, where you've been very proactive about trying to manage the material biosolid locations and end uses. Colorado, we're slowly catching up, but we still land apply quite a bit, and I think people are getting pretty uncomfortable with it. So that's the fun part about what we're talking about here is that we're able to divert that material, that biomass from landfills, from land application, and also from incineration. So really important piece. So what do we do at Living Inc? We convert waste material into essentially a biochar and condition that biochar into a black pigment. We convert those black pigments into inks currently, and that's currently the business model. But I love telling people that we are a pigment company masquerading as an ink company. So our name is Living Ink, but our IP is in the pigment and the production of the pigment. And so we've used that pigment in a lot of different market verticals that are outside of ink, even though we're named Living Ink. So yeah, but this is the whole process that we go through. And we either toll manufacture with groups to process the material, or we do it on our own and have scaled this. We've produced probably close to 10 metric tons. We're probably closing in on 15 metric tons of carbon black that we've sold into markets. And I'll show a little about that. One of the fun things that we can talk about and we have validated here is our ability to call this pigment carbon negative and validate it through third-party ISO certified processes. So we can take this material and convert it into a carbon black and still show that it is sequestering carbon from the atmosphere. It's not such a hot topic right now with the new administration, but we all know that there are challenges, right? There are challenges with the amount of carbon that is in the atmosphere, whether it's from us or from generations past. But the cool, fun thing is that we're actually doing something about it and making a cool product that can be used in downstream applications. So we try to be as pragmatic as possible and recognize that this conversation kind of ebbs or flows, but it's pretty cool to think about pulling carbon out of the atmosphere through algae and other biomass materials and converting that material into a usable downstream product that displaces petroleum. And there's good stories here. So yeah, that's one of the things we like to tout about this pigment. So we do have some IP that allows us to convert our material into a usable product. And I'll go into this in a little more depth, but when you pyrolyze most simple organisms, microbial biomass, what happens to that biomass is that it melts at the temperatures that pyrolysis happens. So 500, 600 degrees Celsius, the simple sugars and simple carbs in those organisms actually melt. It's kind of like the top of a creme brulee dessert, right? You sprinkle the sugar on there, you get a torch, you light it up and you melt the sugar and it crystallizes, right? It crystallizes, you have to break it with the spoon to get to the custard below. It's the same thing that happens with biomass when you just pyrolyze it. RIP allows us to actually think of it as a candy coating, like an M&M. We candy coat the particles in a proprietary salt process that allows those particles to pyrolyze on a unit by unit basis so they don't melt together. And I'll talk a little more about this as we go forward. We get a powder where if you don't apply your IP, the biochar comes out almost like lava rock. It feels and looks like lava rock in a lot of instances, which is very unusable as a pigment downstream. And this is why you don't really see a lot of biochar being used as black pigments because they just don't perform that well. And so, our first product that we ever launched was our pigment product that we call algae black because the biomass is algae, and we're converting into different trademarks as we speak. But it is a pigment that we can send in a powder form, liquid form. I love this picture. It's a picture of one of our techs in back actually processing the material. So we can convert it into a lot of different forms. So what you see on this slide is actual images of actual products that are being sold with our black pigment in it. The Trek bike is a little misleading. If you look hard, you can see the Trek sign on the up tube that is black. That's our pigment and an ink. We wish they would have used more, but we have put it in plastics master batches. You can see that. The leather tanning down at the bottom, that's a Golden Goose shoe. It's a really high-end Italian shoe company. I will never, I don't think, maybe I will buy a shoe for $400 again, but they made that with all of our pigment, which was really cool. It's a fun one to talk about. But we've dope dyed materials. We've actually used our pigment in cosmetics as well. So you can actually go online and find a company called The Unseen. It's a British company, and they are selling mascara called Algae Black, and that is our pigment in that mascara. So that market's interesting one. It's kind of fun to talk about. It's definitely a challenging market. What we currently do with most of the materials turn it into our algae ink product. And so we make different algae ink products for corrugate cardboard, for craft packaging, for apparel, for durable goods like shoes, things like that, and other trims. So if you go in to a store and buy a Patagonia shirt, pair of pants, shorts, the hang tags are all printed in our ink, which is pretty fun to talk about. It doesn't say it on there, but that black is our ink. Same thing with Marmot this year. Same thing with New Balance this coming year. Pretty excited to say that we can make this all into a lot of different products. Ink's made mostly of additives and carriers. So think water, think oils. So for like newspaper ink, that's mostly oils like canola oil or soy oil. Linseed oil is a big one. Most of the inks we make are water-based, which is really nice because we can use the water. But our pigment makes up the pigment component. So anywhere from 5 to 20% of the inks that you see on all the different products that you're using is part of that is the pigment, and that's what we displace. So we do this. Again, all images of products that we have inked, which we really have a fun time with using the product. And we do this mostly because we want to show people that the pigment is capable of standing up as a drop-in replacement to carbon black. And it's been fun working through all the different challenges associated with that. So we have some pretty cool brand collaborations. So here again are some of the products that we're on in the black. We've done quite a deep dive with Nike during COVID. They were really interested in using us and using us on a lot of different products. So we're on 4 shoe lines now. We've probably inked close to 2 million shirts with them. A lot of those shoe lines are actually in boxes that we've inked. So pretty fun to be able to deep dive with groups like Nike and with groups like Kathmandu. So Kathmandu is a smaller apparel brand out of New Zealand. You can find products here, and they've deep dived pretty fun with us too. You can see the back of these shirts actually have our logo on them. You can see them up in the back corner. The A drop is us. So it's been pretty fun to help brands engage with their customers through our material, and just had a great time with it. But in essence, we are a science company, and I'd love to sort of break down some of the science for you guys because we're science nerds at the heart. Scott and I met when we were in grad school getting our PhDs. Scott was looking at predation of algae in open ponds, which sounds funny, but it's a real problem, right? Microbes eating microbes, and growing monocultures is quite hard. It's easy to walk out in a field of corn and pick out the weeds. Try doing that in a microbial soup when you're trying to grow algae. So Scott did that, and I was sort of a gene jockey. I played around with control elements in algae, so try to get them to turn genes on and turn genes off. And neither of us wanted to be professors. We were really interested in that path, and so we just kind of kept banging our heads against stuff and came up with this idea. And so kind of nerded out and start recognizing that biomass pyrolyzed doesn't work that well. And so you can take biomass and pyrolyze it. And like we said, it turns into this aggregate of particles. So it does truly melt together. And I love this picture because it does look almost like dinosaur bones or something like that, right? But it is almost, it's like a glass. It really is. And that's the simple sugars actually melting together. And so taking that biochar that's untreated and trying to pyrolyze it, concentrate the carbons, and do something with it is quite challenging. And if we get into, well, let's nerd out really deeply. These are scanning electron micrographs. So I always love these pictures because, we're looking at 10 microns. The bars here at the bottom are 10 microns, which, what's the width of a human hair is about 25 microns, I believe. So we're looking at particles that were not treated. So untreated pyrolyzed particles. So this is essentially biochar. And on the picture on the left, you can see how many flat surfaces there are. And so the picture on the right shows it pretty well too. It's sort of an aggregate mass. And when it comes down to color, black is essentially the absence of light, right? And so if you have a material that reflects light, you don't get a black color. Even if it's absorbing some, you'll get a shiny black. So think of graphite. Graphite is quite shiny, and that's because graphite is a planar surface of carbon. And so that light bounces right off that flat surface. And this is what we get. And it's problematic for the characteristics that we're looking for to make a good pigment. So the physical properties are really poor. It does not have good porosity. And porosity is really important. I'll talk about that in a minute. The particle sizes are quite large. So think of the ink on a box and think of the depth of that ink on the box. It's quite thin. And so we call them thin film applications. It's so thin that it's probably less than about 10 to 15 microns. So if you have big particles, those particles literally stick out the surface of the printed area. And if you start rubbing things on it, that particle will start breaking and rubbing off on other material. And so one of the tests that we do for corrugate cardboard is rub two pieces of cardboard together. And you can actually imagine how troubling that would be as a production manager, piling thousands of boxes on top of each other and then noticing that the ink from one box rubbed off on another box. So it's quite challenging. And so particle size is really important. Smaller the better. Color. The color is problematic, right? Is that bounces off of those flat surfaces. And is it truly scalable? It's pretty challenging to envision a way that you turn untreated biochar into a viable product without processing the living daylights out of it, and the cost just skyrockets. And so we know, hopefully I've hit this one home, regular biochar, no good, from an SEM perspective to just an image perspective of what we're looking at. Okay, so let's see, am I on the next slide? There we go. Okay, so our core technology is that we add salt surfaces to the outside of these particles. So if you take a look at the first step, we take biomass and we apply coating to the surface of that biomass. It's essentially a salt coating. Think of it as the candy coating. So right now in that lower left-hand corner, The bright green is the salt coating around each particle. The great thing is that when we pyrolyze, so if we go to step 2 and we go through pyrolysis, that salt particle, that salt coating doesn't melt at 600 degrees Celsius. So it stays solid. And it does some really cool things to the particle that I'll show here in a minute. So that process gives us the ability to keep each particle as an individual piece. So whether it's a yeast cell, whether it's a bacillus cell, whether it's a algae cell, we can pyrolyze those particles independent of one another so they do not melt together. And then what we do is we take that salt coating off and we are left with really cool individual particles that are small and have high pores, high surface area with a lot of pores. And that's our core technology. So we patented that. We've been working on that for about 5 years now and really push that technology pretty hard. It relates to something that I'll talk about right at the end as well. So that's our IP. That's the candy coating process. What that does is takes this biomass, so the same type of biomass, and converts it into a very, very fine black powder. And that's the stuff we love because it is a nice, free-flowing, small, dark material that, here's another scanning electron micrograph, looks quite different than the surface of the other scanning electron micrographs that I showed. And this one we just got. I'm in love with this image because I don't get to see the fruits of my labor often. So taking pictures in the small is pretty fun for me. But you'll notice the amount of surface area here. It's almost like I kind of describe it as a golf ball on steroids, right? Is the dimples are pretty deep and those dimples capture light. The light goes into these dimples and bounces around and dissipates that energy as heat. And thus we get the very black color associated with our material. Now, some of these particles are a little bigger. We do some processing after it and they're very brittle, which is really nice. So we can break these materials down into smaller and smaller pieces that allow us to actually print on thin film applications like boxes, like craft boxes, like grocery store, cereal boxes, as well as corrugate cardboard. So we get a product that actually is quite fine and it makes a really good ink. And so this center image, this sort of streak, this black streak is how we test our pigments. We take our pigment, we put it into an ink formulation, and this is called a drawdown. It's a drawdown card. So the card has 3 different components. It has a white upper section, a black strip, and a white lower section. The black strip allows you to understand if you get hiding, which is really important in thin film applications. So can you hide the thing you're printing on? And that's the game. Can you see where the black line starts and where the black line ends is a really important thing that we actually keep track of. And so we get great physical properties, a very small particle size, some dark color, and we are working on scaling this process in a way that's economical. And so this turns into a very good product, as you've seen on all those other images that I showed you guys of commercial products that are being used in the marketplace. And so this is what our IP does. It helps us turn biochar into a usable product that we can actually use. And this is how we test it. All right, so I kind of nerded out, and I'll nerd out a little more because we have done some initial work with biosolids in Colorado. And so city of Loveland, Colorado, a guy named Joe Craigie. Joe's awesome. He's sort of opened the door to us and we sort of poked around and said, hey, is this any interest to you? And I loved his response. He said, I wouldn't have replied to you if it wasn't interesting, Steve. So it was like, oh, okay, so maybe there's something here. And we played around with this with Joe for a couple of years, worked on trying to get funding for it. But I'll walk you through what we did with Joe and City of Loveland Biosolids. So this is anaerobic digestate coming out about 2% solids out of their anaerobic digesters. They're currently land applying it. Costs them a lot of money to get that land applied. Colorado, we do have a lot of land. It's suboptimal land. The Eastern Plains is massive. So we can still do that, but the state is starting to rumble, like, a lot of states that you guys are living in, about this might be a problem. We should look into it. So this is the biomass coming out of the pyrolyzer untreated, so no candy coating. And you can see how granular it is, and you can see sort of more of the grayness. And that's telling us that we may have not processed this well. So we remove the any sort of salts with this acid washing, but this is just a, hey, let's see how it works. And so you can see the hiding problem here on the char, where you can actually identify the black strip. And so this was quite interesting. We said, okay, so it doesn't really work without our intellectual property process. But if you look here on the right side, this acid wash here, you can see it's 100% IP treated, and we get a really nice black. You can see the powder is different than what I was showing you here. Right. So if you just take a look at the left-hand image, the powder goes from pretty granular material to a very, very fine powder. And that's what we're looking for. And here you can see that our hiding is quite well done, and the black is black. And so we test it through an LAB process. It's LAB is a color indicator measurement. L is grayness or whiteness to blackness. A is red to green, and B is blue to yellow. And so it's this sort of three-dimensional measurement of jetness, black to white, and color, A and B. And so the closer to L, the better the jetness or black. The closer to 0 in A to B, the less the color. And so that's a pretty big deal. You can see how that number changes as we go through this process. So demonstrating that we can do this and add value to biosolid material, anaerobic digestate. And I'll throw this out here. This is still sort of pending and cooking. We're hoping to find out about this grant here very soon. But we think we've identified intellectual property that allows us to make good pigment while also converting PFAS not into intermediates, but actually converting PFAS into a mineral form that we can remove fluorine out of the system. So we're really excited about this. I was hoping to know about this grant before I actually had this. So Janine and I planned this a while back, and there's been some challenges the Department of Energy has of late in terms of staffing and things like that. So we're working pretty hard on this, just without even their funding. But this one's really exciting. We think we've identified a mechanism to pyrolyze biosolids, make a good black product while also mineralizing the fluorine found in that material. Very early stage. I don't want to talk a ton about it because it's still sort of, we're cooking, but really excited about it and would love to, talk to folks about this and about this problem. Just trying to do good customer discovery well and understand it. So we're really excited about this. We think we're going to get funded. Fingers crossed. We should know in the next couple of weeks. And that means that we will be off and running and doing the R&D associated with it. But our early tests have shown a lot of positive stuff. And there's a lot of support in academia for the concept that we're trying to push forward here. So we're highly confident that that is going to be the case, that we can actually capture fluorine out of streams, whatever form it's in, and remove that fluorine as a mineral, which would give us the opportunity to capture it and potentially use it for downstream applications where that mineral is actually used on a daily basis. So it's kind of cool. It's, I love the conversation of, are you destroying PFAS and PFAS related chemicals? And destroy is a hard word for a chemist and scientist. I'm sure you guys appreciate that. Or just converting it from one form to the next. We don't want to run afoul of thermodynamics. So, being able to convert it into hydrogen fluoride and spit it out in the atmosphere, well, it causes its own problems, right? And the intermediates that you may break down PFAS into cause their own problems. What we'd love to do is actually capture that fluorine and remove it from the system and convert it into a form where people are not so scared about it, right? forms that go into toothpaste, things like that. So we're pretty excited about this one, but it is early stage. So and I just want to throw this second to last slide up here and just say, what I'd love to hear from you guys is just tap into your knowledge, really understand this biosolid space. I know it's very regional in terms of the regulations associated with managing biosolids, but I'm really trying to come up with a strategy on how we'd enter into that biosolids market as using biosolids as a feedstock and the challenges associated with it and how we'd go to market. And I'm a science nerd that focuses in on pigments and inks. My understanding of the biosolids space is quite limited. The exact opposite for you guys. Your knowledge and expertise here is amazing. So, any conversations that you guys are willing to have with me during this event or after follow-up events, I'd love to talk and just learn more about it. So trying to understand the market, also trying to understand the different intermediates that are made in the biosolids process, right? So aerobic digestate, anaerobic digestate, activated solids, and trying to understand that whole space of where this material ends up and how it gets to its end source and the challenges and opportunities. So any information there and any samples, also we play around with samples constantly, and if we can get this PFAS grant, I think there'll be some really cool opportunities to demonstrate the viability of this tech. Also, I don't want you guys to open up your purses, your purse strings, and that's not what I'm asking. But if you have any ideas on other ways to fund technologies like this, we're a team that's really focused on getting ink into the commercial marketplace. There's only 10 of us. And so, I'm decently good at working with the Department of Energy, the National Science Foundation, trying to work with EPA on understanding how we get funding for baseline R&D to demonstrate our tech. But, if any of you have any ideas on other opportunities out there, I'd just love to hear that as well. And yeah, with that, I'll just say reach out, shoot me an email. My birth name is Steven, Stevan. I go by Steve, but Steven at livinginctechnologies.com. You can find me on our website. Got a LinkedIn handle as well. So, love to hear what you guys have to say. I really am interested in listening to your stories more than me tell stories. So I know I just monologued for a solid 40 minutes. So with that, I'll say thank you and open the floor.
All right. Thanks, Steve. Yeah, I think we have a hand raised and a couple of questions. I think people want to learn more about commercial
Sure.
black, carbon black too. But I do want to just put out there that we're still major supporters of land application here, but we need a fourth leg of the stool, a fifth leg of the stool. So we're all rooting for you. All right. So let's see. I have a couple of folks. We'll go with the raised hands first here. Chad Whiting. I can unmute you. Go ahead, Chad.
Can you hear me?
Yes.
Hey, Chad.
Great. So funding sources, there are a lot of companies out there that don't make products or run big fleets that need to reduce their carbon footprint. So if you can prove you're reducing their carbon footprint by using something like biosolids to reduce, remove carbon for greenhouse gas emissions for that type of thing, then that might be an avenue for you to gain some funding as well. So like if you have a small engineering firm and you're flying employees all over the country, those those type of impacts from carbon footprint are what they have a hard time mitigating. So it might be an avenue.
Sure. Yeah, no, that's interesting. Yeah, if you have any direct contacts, you think people that might be interesting. Yeah, love an intro there just to have a conversation. But that's a good idea. Thank you.
There is a company called Crew Carbon that does something different, but they use like they're taking carbon out of the wastewater using an alkalinity source, and they came to us, and that's how they get their funding through private companies. So maybe
Interesting.
Yeah, carbon
Crew.
credits. That's a
Yep.
big thing.
Yeah.
Thanks.
Okay.
Thanks, Chad, for chipping in on that. So Mike from National Grid is asking me where the predominant carbon black supply chain now. Where is it? Like what, China? Where Where's that coming from? Tell us a little bit about carbon black.
Yeah, carbon black. So there are carbon black facilities in the United States. There's a lot in Canada, and there are a decent amount in East Asia. So yeah, it's quite distributed, but often what you see is carbon black production happening where carbon black use is happening. So like a lot of other industries, right? So there's actually quite a bit in Asia currently.
Okay. And Mike actually put in a link to a critical mass grant available through the Mass. That's the CEC something energy center. So yeah, check that out.
Oh, okay. Yeah, I see it. Thanks.
So I had a quick question. You
Sure.
mentioned the treatment facility you were working with in Texas. Was it Texas or Colorado?
Colorado.
Oh yeah,
Colorado.
Colorado, which is where the Water Research Foundation is. So I got to connect you with them.
Yeah.
But you mentioned it was 2% solids,
Yep.
so there's like a real liquid stream. So you're able to deal with liquid sludges without
We
having to
are.
dry them.
Yes, yes. We actually, that's how we apply our intellectual property is in a liquid stream. So of course we want solids concentration as high as possible, but not much higher than what is pumpable, say 15% dry solid equivalent. And so, yeah, we like the liquid. I mean, it is tough to get microbial biomass away from the liquid. I'm sure all of you guys deal with that on a daily basis, but our intellectual property is applied in a liquid state.
Oh yeah, that will be really good because there's a lot of small decentralized treatment facilities out there that are still generating liquid sludge stream. So that's great. Good information.
Yeah,
Uh,
we're trying to understand how we can be as modular as possible because we know, just like everyone here, I'm sure, shipping water is a killer in terms of
yeah,
cost, right? Water is heavy. So how do we get to a system that is modular, capable of being mobile and moving from one location to the next to make an intermediate product that then is solid and dry and is shippable in a way that we can actually solve some problems around the shipping of water, which is, yeah, why waste in a lot of instances, I'm sure with you guys as well, is costly.
yeah, that's a good model to continue down that path. I think that would be at least for treatment facilities. Any other questions, you guys? Like I said, I want to make some connections for you.
Okay.
Uh, and yeah, we're really all rooting for any new solutions, especially things that might deal with PFAS. So good luck with that grant.
Thank you.
And
Yeah.
when you hear about it, if you could just let us know, we'll spread the word. Maybe we can find some help for you,
Yeah, that would be awesome.
collaborators.
Yeah. 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 I'm excited about it. Let's see how excited the Department of Energy is about it. So
Well, I hope they are. But yeah, that was good, geeky, nerdy stuff. It was a great presentation.
good.
Thanks, Steve.
Good. Of
Again,
course.
we're wishing you all the best of luck, and let us know how we can help if we can. I know NEBRA members are always looking at the future technologies, so
Okay.
rooting for you. And thanks to our sponsor today, Underwood Engineers, and thanks to everyone for attending. I will send out the slide deck and the recording next week to everybody who registered. Next month, we're going to lunch and learn with one of our members, the Montague Clean Water Facility, to hear about their very cost-effective dewatering upgrades that they did mostly in-house with a big return on investment. So for the small facilities, there's hope. But as always, if there's something you want to lunch and learn about, shoot me an email, let me know. I'm always looking for suggestions. Thanks again for attending today. Happy Friday, everyone. Have a great weekend.
Thanks, everybody.
All right. Thanks, Steve. Have a great
Yeah, of
day.
course. Yeah,
Go
you too,
Sox.
Janine.
All
Thanks.
right.
Thanks for having me. I really appreciate it.